Yeah, the title of the presentation is a question. And I don't have the answer, but I'll guide you to maybe some possibilities to do it in another way. For those of you who are not very familiar with the field sampling, I've put in sort of the procedure that at least is used by the RIVM, the Institute of the next speaker actually. So they core a hole towards the upper meter of groundwater. Then a tube is put in, and of course they have to register their location and measure some field parameters. Some more field parameters. They have to get the sample through a filter. And then the transportation cooled towards the laboratory for analysis. And there's much more work to do. So in a short evaluation of that, it's quite expensive, heavy work. It involves many steps. It can implement a lot of errors, and it's slow. Usually you have your results weeks after. And does it actually provide the information that we want, that we need? Sometimes, but sometimes also not. I've seen fields, this is an example where the spatial variability in the concentrations in upper groundwater is quite large. Here it's a 1 hectare field, and it's, well, as you see, it's flat, it's managed the same, the entire field, so there was no obvious reason for differences, but we found concentrations from 0 up to 200 milligrams per liter nitrate. And we had to do 61 samples in this 1 hectare field to get that picture. And then there's the temporal variability, especially in the upper groundwater quality. Well, this is an example of an experimental farm where researchers try to prove that even when we have a soil that's vulnerable for leaching of nutrients, we can achieve the water quality target of 50 milligrams per liter. So that experiment started in 1990, and as you can see, they were very successful because, well, here they had a party because they were below the 50 milligrams per liter. But afterwards, well, they're still implementing new best management practices, but concentrations went up again. What actually happened here is that there were 3 quite dry years, and during that year the recharge was not really a lot, so the nitrate sort of was stored in the unsaturated zone. And 1989 was a very, very wet year in the Netherlands, and then that store was leached, was accelerated towards the groundwater. And you can perfectly model that. Actually with this I copied Leo Bouwman's a little bit. We just put a conservative tracer with a constant concentration at the upper boundary of the model, and then as a result, because of the weather variability, you see this kind of variation. So here, this is the trend that was caused by the change in land management, but these variations are caused by weather variability. We have to take that in mind. And then, as a final thing, when we look in the subsurface when sampling, what is actually the water that we are sampling down there? Is it really a good mixture of the upper meter of groundwater, or are we, by pumping, sucking up maybe water from a preferential flow path from the upper layer or from down there? So those are some issues about does this type of monitoring give you the information that you need? Not always. I'm going to show you a couple of innovations that aren't the answer to all these issues, but maybe useful as an addition or for specific dedicated monitoring programs. So I'll start with maybe you don't have to measure groundwater, because if you have a drained field, sometimes these tile drains can give you a nice average concentration of the groundwater around that tile drain. Well, as you can see here, these are some results from weekly tile drain sampling, and there are 2 with relatively high nitrate concentrations and one with very low. We only understood that after we sampled all those locations here. The one low concentration drain is just missing the two hotspots. So actually there's 3 sampling sites for drains. They give us a better average concentration than the 61 core groundwater samples. Putting that towards a bit larger scale, we think that surface water can also reflect the groundwater composition, as long as you still have a connection, of course, between groundwater and surface water. So during dry conditions, we discharge the deeper groundwater, and surface water resembles deep groundwater quality. And when you go to more wet conditions, then also the less deep flow routes start to contribute to the surface water, and you can see that in the surface water chemistry. Because usually the upper groundwater has a different quality than the water deeper, because usually it's older, it's cleaner, it's purified a bit by the soil passage. So this is used in a more quantitative way by Seibert. He's calling that the REM approach, the repair and profile flow concentration integration model. So you have to have a picture of how much water is each layer in the groundwater or its flow route contributing to the surface water, and then you can combine that with a concentration depth profile. Then you can actually forecast the concentration discharge relationship in surface water, but you can also do that the opposite way. So when you know this, when you have good monitoring data in surface water, you can do this backwards and actually predict this concentration depth profile. But I refer to Seibert if you want to know more about that. Then, more technically speaking, we can also, to deal with these temporal variations in water quality, we can measure average concentrations. For pesticides, we've been using passive samplers for that. So we have 2 types, the silicon sheets and the speed discs. There are many more types, but it gives you a sort an average period, a period of 1 month or 3 months average concentration, which can, especially for pesticides, be very useful because it can be very spiky sometimes. For nutrients, we have some more experiences with these passive samplers, the sorbet cells. They actually, when some of the water goes through this part, captures the nutrient that we're interested in. And here is a salt ratio released, and that's the amount of salt that is released is a measure for the amount of water that went through. So together, this gives the mass, this gives the volume, gives you an average concentration over the period of installation. And we've been using that in groundwater, but also in surface water and tile drain water. More recently, we also made a mounting method for the sorbet cell that enables measuring flow average concentrations from tile drains. So by installing it into a sutro profiled outlet, there's a 1-to-1 relation between the discharge of the tile and the amount of water that's sampled by the sorbet cell. And well, this is one for small tile drains, but we've also scaled it up for the larger tiles that are more common in the US, I guess. Another innovation that we've been using for measuring temperature a lot is using glass fiber sensors, distributed temperature sensors. The way it works, there's a laser sending a light signal into the cable, and it's backscattered, and that's measured here. And you can really measure temperature continuously and at every meter of the rope that you're using, of the glass fiber. So that can give you real distributed and continuous monitoring. And we use that for example, for monitoring aquifer storage systems. So we try to store energy, warmth, by injecting it to the groundwater in summer, and in winter we can pump it up again. And you can check how that works by measuring the temperatures in the water. And I have an example of data that would be nice to have. Oh, that's not working. I'll do it like that. So now you see in green lines actually the timeline of the temperature when infiltrating this warm water into the groundwater. So it's infiltrated via the well. Then there's well, it's actually quite a small step from this temperature sensing to the distributed chemical sensing. The only thing that we have to use are these quite new fiber grating sensors. They are sensitive to strain. When we combine that with a coating that responds to the chemical that you're interested in, for example nitrate, that strain that produces can be measured again with the light and the backscattering in the glass fiber. And yeah, we are quite close to having a coating that is responsive to nitrate. That's worked together with TNO, another research institute in the Netherlands. Then, as a final one, well, this is actually putting something old in a new form. Maybe you're familiar with these kind of test strips. They're also used for swimming pools and aquariums. We've been recently developing it. We are currently testing it to read them with a smartphone. It can be sometimes quite hard because the scale is really the colors are almost the same. And by reading it with a smartphone, the measurement is a little bit more precise and objective. And a big advantage is that we can also share the results immediately. We can send the results and put it in a data viewer on the internet. And this is actually meant to let farmers participate in the water quality monitoring, so that they get a feel themselves for when and where they are losing their nutrients, because they don't have an idea, of course. They have some idea about droughts and when to irrigate because they can see that directly, but when and where you lose nitrates, it's hard to see. So this may help. It's very cheap, and well, the app is going to be open source and free, but I'm thinking about a couple of months. So, and then I was sort of dreaming a little bit about the curiosity that we're putting on Mars, and it's just a bit surprising that we are we core in rocks and take samples and analyze it on site. You can do that on Mars, so how difficult can it be to make something like this for groundwater? So here's my first design of that. There you go. And it would be also good if he sent his data. Of course, this is a robot mower, but so will our traditions for groundwater monitoring survive towards the 21st century? I hope not, because by the time I'm under 20 years old and I just want to retire, sit back and relax, and let the sampling be done by a robot. So with that, I think I'm quite on time. Thanks for your attention.
Questions?
Hi, I was wondering if you could explain or talk a little bit more about the nitrate app that you showed a couple of slides ago. It seems like it has a potential for kind of rapid at-home testing, also for issues like domestic wells.
Yeah, that's possible. Yeah, there's not really much more to say than I already did. It's as simple as that. And of course, it would need a dedicated viewer for that application that shows the map of the area that you're trying to get the people to measure, and it's also nice to add some background information like well, whatever may influence the nitrate concentrations. So.
I'm going to keep you on the same app again. And one question is, it seems very interesting, and I heard it was open source, so that's definitely something that I would like to experiment with. How do you do about the data? So I think when you go and measure the data, or the farmers do you have some secret database or something that is not too public, or how is it the data handled?
At the moment, the data is sent to our server, and the map looks for new data on the server when you access it. But that can be we can put a password on that. That's no problem. And also the farmer has the option not sending his results. So he's asked, do you want to send his results? And he can add some information, what type of water it was, maybe a remark, and then send it. So yeah, that's also if he just wants to show it and measure his beer or something, then we don't want that in our database.
Yes, thank you. I have two questions, also one on the app. I'll start with that one. Are you also considering other parameters than only nitrate, like electrical conductivity with a simple add-on to the smartphone, for instance?
In the app?
To the app, yeah. Now you're only measuring nitrate, but I think in coastal areas a lot of people are interested in the electrical conductivity or the salinity, for instance, which you can also easily measure and plug in.
Yeah, we're thinking about that. It's this is based on test strips, so basically all test strips available could be
chloride
added.
as well.
Chloride is well, I ordered some of those test strips lately, and it's a bit strange thing. It's a sort of like a temperature sensor. Yeah. It's a different way of reading. But there are also you could also combine it with some smartphone connected connectivity sensors that are also being developed by others. Yeah. And we are adding pH in the coming months.
Yeah. One other question was on the pesticides you measure with the continuous flow-through cell. Is there not any degradation taking place over time, which may influence the analysis in such a cell?
I'm not entirely sure. Yeah, that may happen under certain conditions. I just tested in one catchment. I've heard also of some complications when it's when you're measuring a bit brackish environments. But well, it's something it's quite easy to test for your own waters by just loading up a sorbet cell with a known concentration and yeah, letting it maybe process for a while and then send it for analysis.
It's interesting to see your idea of a nitrate app. Probably will enable the local community people to participate in monitoring. I was just wondering, what's the accuracy in the measurement and the detection limit that you get from this kind of dipping and then do the analysis?
Okay, yeah, I'm thinking, knowing this, I should have dedicated my entire presentation on the app. Yeah, that depends on the strips that you're using. So that's the ones that we are currently using are strips of Hag, and they range from 0 until 100 milligrams N. And yeah, I think for the values below 1, 2, yeah, there's of course some uncertainty. It's also, you should see it more as an indication of the nitrate concentration, especially at that range. But when we tried it, actually we were always right whether it was above or below the drinking water limit. That was always correct. So that's a level of concentration that you can capture quite well.